All right, so space unit, Science 9 space unit. We're going to get started on the space unit. You should have some notes in front of you, the blank set of notes there that you can fill out as we move through. And so what we are looking at here is our universe, exploring our universe. We're exploring the sun, the moon, the stars, our solar system, different galaxies and pieces of the universe, talking about the creation of the universe, the distant past, and what's going to happen in the distant future maybe. We're going to explore too. You guys have some projects that you're going to start if you haven't started already on different kinds of space exploration. You're going to dig deeper into aspects of the universe. I was just outside last night looking at the stars and looking at things in preparation for this. So I will give you some things to do, and I hope that you guys get to explore a little bit, just the stars and the constellations and things like that. And so let's get going on this. Your first page there should be 9.1, Human Interest in Space, and this will mirror your textbook, the Pearson Sask Science 9 textbook. A lot of these notes are taken from the textbook there as well. So there are many theories about how the universe began. If we talk about beginnings, there are theories about how the universe began. Obviously, the universe exists. So we either have two options to believe that the universe has always been, that it's eternal and always has been here, or that it had some kind of beginning. And those are the basis of the two main theories we're going to talk about just briefly here. But some scientists in the past have claimed that they believe the universe was eternal. So for a long time, scientists thought, a beginning to the universe doesn't seem reasonable, so it would seem that the universe looks to be really old, so maybe it's just always been here. And but now the universe they've discovered is expanding. And so with that, that's the main piece of the puzzle here. Many scientists now believe that the universe did have a beginning, because the universe literally is stretching out. Okay, every second it's stretching out. And it's getting, the outer edges of the universe everything in the universe seems to be getting further and further away from us as we're able to observe. And so scientists have extrapolated that backwards. And you guys can close your close your Chromebooks there. We don't need them right now, thanks. Just stay focused here. You can look stuff up afterwards. Okay, yeah, close them right down. Scientists have extrapolated back. So that means that they say, okay, if it's expanding now, maybe some point in the past it was smaller than it was now, and then if we keep going back, it seems like maybe that it has come to this one kind of single small point, and that's where it was in the past. And so a lot of scientists believe that the universe now did have a beginning. And they call that the Big Bang, right? And we're not going to talk too much about that right now, but the Big Bang is what secular scientists, believe was the beginning of everything. And they believe that nothing exploded and created everything, which is a bit of a stretch, right? But there's all sorts of different ways they're trying to work around that. But the other theory of beginnings that we need to study as well, we need to be aware of, and we've talked a little bit about this already, that there are accounts in history of a creator and creation. And if we look at what the Bible has to say about the universe, the Bible explains that God created the universe out of nothing by his word. And if we look at Psalm 33:6, by the word of the Lord were the heavens made, their starry host by the breath of his mouth. The Bible's pretty clear, and other places too. It says, by faith we understand that everything that we see was made from nothing. And that lines up really with what scientists believe now. The science seems to be catching up with the Bible in some respects. So basically the two beliefs that we are faced with are nothing created everything, or God created everything. Nothing exploded and created everything accidentally, or God created everything out of nothing with some purpose. Okay, those are the two big ideas here, and I'll let you guys think a little bit more about that and what really you want to believe about that. But it's generally accepted that at one point there seems to have been nothing, and now there is something. Okay, so the study of objects and the phenomena in space is called astronomy. We're going to focus on what we can see, what we can observe. We're going to focus on the development of the models of different things. And it's going to be really cool to examine the stars and the planets and solar systems and galaxies, black holes and comets and meteors and all that sort of stuff in this unit. So astronomy, the study of objects and phenomena. Now, phenomena are just like things that happen in space, things that happen. So that's astronomy. Objects that we observe in the sky are called celestial bodies. Celestial. C-E-L-E-S-T-I-A-L, celestial bodies. Okay? All right, let's talk about constellations. You all know what constellations are. It's an arrangement of stars that appears to resemble some kind of form or something like that. So one of my favorites, and the one that you can see, probably the easiest in the sky, I would say, is the Big Dipper. The Big Dipper. So a dipper, well, it's big because it's in the sky, covers half the sky. But a dipper is kind of like a big spoon, like where you dip, a scoop where you scoop soup or something. A Big Dipper. And so the stars and they're really bright. They are kind of like this compared to the other stars in the sky. They're quite a bit brighter. So they form a handle and then this big kind of scoop end. It's called the Big Dipper. And there's some cool things about the Big Dipper. I believe it's these two stars right here. I don't have this in the notes, but I believe it's these two stars that point to the North Star. We'll talk a little bit more about the North Star, but the North Star is the only star in the sky that doesn't move position as we look at it. And there'll be reasons for that. We'll talk about that a little bit later. But all the other stars, through the course of the night, through the course of the year, you look up and the constellations are in different spots. So as the Earth rotates, we get a different picture of the sky above us. And the constellations are still visible most of the time, the ones that we can see, but they're in different spots in the sky. Did you know that the southern hemisphere has a whole different set of constellations than we do? Did you know that? The southern hemisphere is the southern half of the Earth. So everybody south of the equator would be looking at space from the south end of the globe, and they're looking at stars that we don't see. They have different constellations. And they wouldn't be able to see some of the constellations that we see because we're on the top half of the Earth, and we're looking up. They're on the bottom half of the Earth. If you think about the southern hemisphere as the bottom, they're on the bottom half. They look down. Isn't that cool? So there's a lot of different constellations in the southern hemisphere. Okay. Another example from Scripture, Pleiades and Orion. Job 38 says, can you bind the chains of Pleiades or loose the cords of Orion, as God addresses Job in his questioning of what God seems to be doing. And God's basically reminding him, hey, listen, can you hold on to the stars? Like if you create these things, do you bind these up? Do you pull these stars together? The cords of Orion, Orion's belt. Are you the one that can do anything with these? Just reminding Job of kind of how small he is and how big God is to create all this. So this is a little picture. Now it's a bit of a fuzzy mess there, but if you take a picture of Pleiades, it's also called the Seven Sisters as kind of a nickname, and there are groupings of really bright stars. And you will see this in the night sky and it's quite faint. And here's the thing with Pleiades. When I look at Pleiades in the sky, if you actually look directly at this grouping of stars, it's almost like they fade away and you can't see them. But if you look away from them and try to focus them on them off the periphery of your vision, like if you look just next to where that grouping of stars is, they're a little bit brighter in the side view of your eyes. It's weird because I don't know why that is. But if you kind of look away, you can kind of see it on the periphery, and you see this grouping of stars. As soon as you look over there, they seem to fade away, and they're a little tougher to see. But anyways, it's interesting. I think on the next page I have, here's some other pictures too. There's a Pleiades in the sky there. And Orion, okay, so I grabbed this picture off the internet. Obviously, we don't see, these caricatures in the sky, but Orion is also a constellation that is quite noticeable in the night sky. So these three stars that make up Orion's belt right here, and I'll just kind of maybe try and highlight those in red. Those three stars that make Orion's belt are pretty bright. And then these stars here, there, and those ones there are also pretty bright. So you can kind of see that grouping of stars pretty easily. These would be a little bit fainter over here, these stars. And yeah, you can kind of see maybe some stars over there, but these are the real bright ones in the middle. Here's Pleiades over here. So if you're looking at the night sky tonight and you want to see Orion and Pleiades, what you do is you find Orion first. If you can't see Pleiades, you find Orion first, and the belt. So look at this belt here. See the direction of the belt? The three stars kind of go like that. If you extend that into space like this, Pleiades would be just above this line, or if it's kind of like a curved belt almost. So this curved belt, if you have a little bit of a curved line, it points right to Pleiades. So the three stars that make up the belt of Orion constellation would point to the right over to Pleiades over there. And then this Taurus here, this can be pretty bright. So kind of these three can be pretty bright as well in the night sky. But anyway, so constellations kind of loosely resemble, it depends how many of the stars you can actually see on a given night, but they loosely sort of would outline some kind of maybe recognizable form. Sometimes it's a bit of a stretch, but. Any questions so far? So also in the constellation of Orion is one star that I want to talk about. It's pretty cool. It's one of the biggest stars that we've come across. It's not, technically it's not the biggest star in our galaxy. Also all these stars that you see here, all these stars that you ever see in the night are only stars in our own galaxy. Frozen. How's that? Unfreeze, okay. So yeah, so when you look up at stars, these are stars in our galaxy. You've heard of other galaxies. We can't see stars from other galaxies. We can't even see all the stars in our own galaxy. The stars that we see are all in our own galaxy. And you'll see just how big our galaxy is compared to our solar system, compared to the universe. But the stars that we're able to see are only the ones that are in our galaxy. So Betelgeuse here is one of the biggest stars that we have come across. It's super bright, and it's the shoulder. So we go back to the other, it's the shoulder one, okay? It's the shoulder star here of Orion. So there's the belt. This is Betelgeuse. And it's quite far away, but it's super big and super bright that it looks like it's, you know, as close as many of these other ones. So that's where it is on the shoulder. And take a look at this here. This is a bit of a size comparison. Here's the sun down here. This little dot right here is our sun. So of course, we are barely we would not even be a dot that's recognizable on the little picture. Aldebaran and Regal, and I think this is Antares over here. Yeah. And then Betelgeuse, look at this, huge, a huge, super red giant here. So this is an immense star. Interesting how our sun looks quite a bit bigger than this star, right? If you know the sun in the sky, right, looks huge compared to a little star in a constellation. But because it's so far away, it actually looks quite a bit smaller, and because of its brightness and things like that. Yeah.
So basically, we're atoms of the atom in the universe.
So I have this little YouTube video I want to show you. It actually talks about what would it actually be like, because they actually think that Betelgeuse here is actually pretty close to going supernova. They think it's actually pretty close to exploding, like dying, like being gone. And so if it went supernova, this big thing would be quite the sight in our sky. And so there's actually a little simulation I'm going to show you here and you can probably look at this afterwards if you're watching this video later. You can check this out on my site or click the link that will be given. But let's take a look at this simulation before we move on. All right, so here's a YouTube video, Betelgeuse explosion realistic simulation. I'll just play this and I'll just cut the music there. But remember, so here's Orion's belt. There's Betelgeuse right there. There's Betelgeuse right there. And if it actually went supernova, this is what it would look like in the night sky. It would almost completely overtake the night sky. It would be about as bright as the moon, if not a little bit brighter. And it would be so bright and so intense that we'd actually, okay, so there's a comparison with the moon. So it would be brighter than the moon, looks like. About the same looking size, but you could tell something's gone on here, right? This is not just reflecting the light off the sun. This is generating its own powerful energy. Not sure what the radiation would do to us if it's too far away, but the cool thing is you'd actually see it in the daytime too. You wouldn't see any other stars, but it would be bright enough that you would be able to see it in the daytime. So if this thing goes supernova in our lifetime, we're going to know about it. We're going to know about it. Cool, eh? All right. So big star, and stars can explode, and that's called going supernova. Supernova. Summer solstice. The sky is used to mark the passage of time and seasons. Okay, so the summer solstice is around June 21st. And I say around, we kind of throw out that number, but really it can fluctuate, kind of a day here, a day there. But the summer solstice is the longest day of the year in the northern hemisphere. So we're in the northern hemisphere, so let's talk about us. It's the longest day of the year. This marks the Earth's greatest tilt towards the sun. Okay, so I'm going to zoom in on this little picture here. I think you have a small picture as well in your notes there. But here's the Earth, okay, and the Earth revolves around the sun, so it goes around the sun, and the sun is here, and the sun is not completely in the center of the Earth's orbit. It's slightly elliptical, which means that the distance from the sun to the Earth, it's at different times of year, it's actually different. So we're a little bit further away at times of the year, a little bit closer. So the orbit around the sun is not the sun is not perfectly in the center of our orbit. Okay. Now for us, the tilt of the Earth's axis, it's not the axis of the Earth is not 90 degrees to the sun. It's actually like 23.5 degrees. We'll talk a little bit more about that. But we're on the northern hemisphere here, so up near the top. So in the summer, we're actually further away from the sun than we are in the winter. Did you know that? A little bit further away. But because we are tilted towards the sun, this is why we have more hours of sunlight. This is why it generally gets hotter while we're over here on this side of the sun, because there's more hours of sunlight. The sun is higher in the sky. So in the summer, right, if you face kind of the south, the sun rises in the east over there, and in the summer it comes almost right over top of you, right? It comes really high in the sky, and then it takes a long time to go down to set, because it has this long way to go across sort of the top of the sky. In the winter, so we're approaching winter now, but in the dead of winter is when we get the least amount of sunlight. And if you face south and you kind of map the sun's path in the winter, the sun is pretty low on the horizon. So that's why it's dark quite a bit later in the morning, because the sun is rising a little bit more south, and so it's not up in the sky as much. It's pretty low in the sky for us. And then it goes down, and that's why it gets dark at 5 o'clock at night, because the sun's already down below the horizon, because it has such a small... So in the summer, the sun appears to be higher in the sky. In the winter, see, here's us again. In the winter, the sun appears to be low. You see, here's like the middle of the sky. Here's like the middle of the sky. So the sun is pretty high in the summer, but the sun is really low in the winter. So we have few hours of sunlight, less direct sunlight, so everything's a bit colder. So the summer solstice would be when the Earth is right here, and it's the longest day of the year because we're tilted towards the sun the most. Okay? And here would be the winter solstice, when it's the shortest day of the year. The shortest day of the year for us. Okay? Any questions there? So the winter solstice would be the shortest day of the year, and that's around December 21st. This is the Earth's greatest tilt away from the sun. So let's take a look at this little diagram here. And if the Earth was tilted this way, and here's the sun over here, when the Earth is directly above the Tropic of Cancer right here, that's the longest day of the year. So for us in the northern hemisphere, so we're right about here somewhere, okay? This is going to be the longest day of the year, right here, summer solstice. In the winter solstice is when the Earth, basically we're on the other side of the sun, and let's say the Earth is still, I don't know if you guys can see this real well. Here's the equator, here's us. Oh, that's a really bad circle. Can you guys see that? Ish? Let me see, I'll get a different color for you. How about yellow? Whoa. It's bright, but something is happening. The computer's not happy with us. So we're right here, and the sun is over here, right? And so for us, the Tropic of Capricorn, that would be this sort of imaginary line on the Earth, and the sun is directly above that point of the Earth. And so for us, see how low the sun is in the sky here? Like it's really, really low. Here's straight up into the sky for us. It's really low on the horizon. So that's our shortest day of the year. Now the equinox. Equinox is equal. I'm not sure if I have a slide for that. Let's just see. Equinox. Nope. So the equinox is when we are, and then we'll go back to this little diagram here, right here. So this is the equinox, when we have equal day and light hours. So it's between the shortest day of the year and the longest day of the year. 2 times a year we have equal day and night hours, equinox. Yeah, and we're in these positions over here for the equinoxes, okay? And equinox, equal, think about equal. Awesome. Okay, prediction of seasons. So someone, you asked, Nathan, how we know these things are happening. Well, you can kind of measure the daylight and things like that. Ancient cultures have created markers for the onset of seasons and to mark calendars. And some of these famous markers that we have around the world and even in our home province here are examples of the Moose Mountain Medicine Wheel. So this thing right here is a huge structure, and it would use the shadow of this mound, I suppose, to indicate sort of what season we're in, when the solstice would be, and stuff like that. Stonehenge is a lot of mystery around Stonehenge, but it's one of the most famous sort of structures. These are people in the diagram, in the picture here. So these rocks are super huge. Some of them have fallen down and whatever, broken up, but it appears to have been some kind of sort of structured to either mark seasons and things like that, or something. There's a lot of mystery shrouded around Stonehenge, but it's also one of the more famous of the markers that have been made. So I would encourage you at some point to look up, Stonehenge and the Moose Mountain Medicine Wheel to do a little further study in those. But cultures have realized the importance of marking the onset of seasons, when they start, when they finish, and all this sort of stuff. And it's kind of like a big calendar they made on the ground. Okay. All right, how are we doing here? Well, let's keep going here. So using the stars for navigation. So what use can the stars have for us other than to be beautiful and to look up and to appreciate the wonder of nature and the goodness of God? Devices like the sextant and the quadrant helped use celestial bodies, so we're talking stars, maybe the moon, but usually stars, moon moves too much, to determine location. And this was very helpful kind of back hundreds of years ago, when sailors were trying to navigate the ocean and trying to know where they are, because there's no land, there's no roads, right? There's nothing to see other than the stars. So as the stars change, you can use these devices here to find out where you are, particularly for sailors in the ocean. Now, Polaris is the North Star, I believe. So remember the one that doesn't change position, right, in our sky. And so they would compare the positions of stars to where they are and to where Polaris is, and the horizon would be, and so they would be able to kind of know how far they've gone or if they're off course or whatever. Okay, questions? So the sextant and the quadrant, ancient measuring tools for sailors. You've seen these in the movies. They basically, you line up, a star here, and you can calculate what the angle is from the horizon and so on. And that helps you determine sort of where you are. Okay? So the sextant, look at this, the sextant, quadrant, there'd be different shapes, I guess, calculating sort of different things. But, anyways. So again, that can be, you can devote some further study to that if you're interested. All right, describing positions in space. Okay, so altitude and azimuth. Okay, altitude and azimuth describe coordinates of celestial bodies. Altitude is measured from the horizon, which would be 0 degrees, to the point directly overhead, which is the zenith at 90 degrees. So if you're measuring altitude, it's basically the height above the horizon. The azimuth refers to the position of a celestial body from due north. So if you're talking about the moon, let's say, and CB is celestial body. If you're talking about the moon, okay, you would first of all have to know where due north is. and sailors would, would have a compass or something like that where they would be able to find where due north is. And so from there, they would be able to, count how many degrees over and how many degrees up would be the moon, and they would be able to compare that with their star charts or their moon charts or whatever. They would be able to know sort of whereabouts that they would be. So again, altitude is the height above the horizon. Azimuth would be kind of left or right from due north. And they would kind of start at north and go in a clockwise position. So 180 degrees azimuth would be starting at north, looking at north, and then going exactly halfway around, and that would be due south then. That would be due south. Okay? So that's why these instruments here would be pretty good to know your altitude, and you'd be able to calculate different angles, which angles would be pretty important in navigation back in hundreds of years ago. So here's a little shortcut. You can use just your fists right here, and you can actually calculate the altitude and azimuth of a star or the moon. If you know where due north is, you just line up your hands, and let's say we're trying to find out the coordinates of where the moon is. Each full fist would be about 40 degrees, and each finger would be about 10 then. So about 10 degrees. So your fist here with your 4 fingers up, however many fists you'd go over to so that you're directly underneath the moon, let's say. So this would be exactly 4 fists over, so this is 40 degrees azimuth. And then how many hands up from the horizon? So this would be 20 degrees altitude. So you could actually do a rough measurement of altitude and azimuth for the moon or the stars, things like that. Okay? All right, so that brings us to the end of section 9.1. Here are the homework questions from your textbook. So you want to jot those down, and those will be questions that will help you to know if you understood and were able to process kind of what we did in this lesson.